So this is just an introductory few slides on the basic concepts of radar imagery and synthetic aperture radar imagery. To get started, so like I was saying, we are familiar with Landsat imagery, right? So so just excuse me, this is a little, this is a small image on a slide, but the point here with this figure on top is all the Landsat satellites so far. This figure shows the various bands, various wavelength bands that the Landsat sensor senses. So if you remember all those bands that each of the Landsat image has, they all come from different parts of the electromagnetic spectrum, like it is shown in this. So the horizontal axis is the wavelength. So there's band 1, 2, 3, 4, 5, 6, 7, and so on, all the Landsat bands as well. So this is the range of wavelengths that Landsat bands covers. But if you think about the electromagnetic spectrum, that has a much larger span, right? The wavelength goes from much shorter wavelengths and gamma rays and all of that, and much longer wavelengths like in radio waves. And here, right here, is the microwave band. All the microwave signals are in this range of wavelengths. And if you notice, somewhere in the middle here is the visible spectrum, which we see as humans, and they form part of the Landsat bands as well. Now, if you think about it, so the Landsat bands, which go from about 400 microns, 400 nanometers to about 13,000 nanometers in this figure, they map to just about this range in the electromagnetic spectrum. A little bit of the infrared and a little bit of the visible spectrum. As you can see, the microwave bands are entirely outside of that. So Landsat bands, the range of electromagnetic spectrum that the Landsat satellites sense, are entirely outside the range of wavelengths that the SAR imagery captures. So that right there is a fundamental difference between Landsat bands and SAR bands. And I don't have the data here for Sentinel, but the comparison would be somewhat similar even for that. So the take home is that optical imagery in satellites, they span a range of about this much, and that is entirely different from the range of electromagnetic spectrum that SAR bands capture. So just a little deeper into how radar and optical imagery compare. So on the left is the highlights about the radar imagery. For example, radar imagery, just simply because of the fact that they are in the microwave range of the electromagnetic spectrum, they are much less affected by atmospheric effects, which is very different from optical imagery. I'm sure any one of you who's worked with Landsat know that atmospheric effects have to be corrected before you can start using the surface reflecting products. So going from raw captures of the Landsat imagery down to the surface reflectance, there's a lot of atmospheric effect correction that needs to be done before they're useful as surface reflectance. But like I said, radar imagery, they have almost very minimal atmospheric effects. The other important thing to keep in mind is radar imagery is active sensing, while Landsat and other optical imagery are passive sensing. And the key point here is that optical imagery, the satellites just fly by, and the sensors are just sitting on the satellite and sensing the electromagnetic radiation signals that they sense reflected off the ground. So they're just passively sitting there sensing what falls on their sensors. But radar imagery, they are active in the sense that the satellite, as it is flying by, it actively emits radar imagery, microwave energy, and it waits to sense the reflected signal back from the ground. So in optical imagery, there is no transmission of any signal, but in radar imagery, radio waves are actively transmitted from the satellite, and the sensor is waiting to pick up the reflected energy from the ground. So in that sense, that also is a very significant difference between radar imagery and optical imagery. Moving on, so the other important difference is that radar imagery, because again of the wavelength of the signal used, they are all-weather imagery and day and night capabilities, since they don't depend, for example, on visible light. They can see even at night, and since they don't depend on visible light, clouds don't interfere with their signals as much as clouds interfere with the optical imagery. So because of those two effects, the radar imagery can see through clouds, they can see at night, but optical imagery, of course, as you all know, they can't see through clouds, and of course not at night as well. The radar imagery, the actual signal that we are working with at a pixel level, they are what are called backscatter values, and this backscatter is sensitive to target properties in ways that are different from optical imagery. We'll get into a little bit of detail about this, but I just want to put it up there here as one of the key differences between radar and optical imagery. So radar imagery depends on backscatter, and the backscatter depends heavily on the target properties on ground, like, for example, structure and dielectric properties of the target. There are a few disadvantages of radar imagery as well. A few of them I've listed here. The data basically can sometimes be hard to interpret. And this is particularly so for many of us who come from having worked with optical imagery more, and since the data in radar imagery is fundamentally different in the way they are captured. Yeah?
Sorry to interrupt. Let's try to figure out this technical issue.
Yeah.
You're presenting your screen, but for some reason on the YouTube live stream, it's not showing up as the main window. I've tried to present to everyone, which is what I normally do.
Is
But
this
it's
better
not,
now?
no, I'm not sure if it's something on your end.
Okay.
As an intermediate sort of solution, Dhrutiraj, if you're there, can you share your screen, because the live stream seems to be showing your window.
All right, I will do that.
Yeah. Okay.
Okay. So right now, Prithviraj, I'm on the slide titled Radar versus Optical Imaging.
Okay.
Yeah, and just hit space one more time so that the disadvantages at the bottom animation also shows up.
Yeah, we see the slides. So
okay.
Okay, great. Thanks, Greg. So I'll continue. So all these slides are. I hope you are able to follow along since you have the link to the slides out there, all of you in the audience. So moving on. So like I was saying, there are a few disadvantages with the radar crossing as well. Some of which is largely because many of us come from thinking about remote sensing from the optical space. So it can be hard to interpret. Some technical reasons why there might be difficulties in interpreting radar imagery is the sensor is side-looking, and like I said, there are topographical effects on the signal that's received, and also there are sources of noise like speckle noise. So we'll get into a little bit of detail about all of this, but again, I just wanted to put it all out there in one slide about the main comparisons and some of the disadvantages of radar. So next slide, Dhrutiraj. In this slide, there's a figure, there's a cartoon. So there's the cartoon on the left and the right. So this is how SAR imagery is captured. You can think about it as a shuttle that's flying over, and it has a sensor and a transmitter. So the transmitter transmits the radio waves, and the sensor receives it, and that's the sensed signal. So what's on the left is, let's say the shuttle was transmitting top down, like so if it was looking top down and it was transmitting also top down. So you can see that if there are two targets A and B on the ground, then the time that the signal takes to go and get reflected back from both of those targets are the same, right? So from A, It might come back at time t0. It will come back at time t0 from B as well, because the distance from A to the shuttle is the same as the distance from B to the shuttle. The thing here to note is, since the SAR imagery depends on radar radio waves, microwaves, what it is really sensitive to is phase differences between the transmitted and the received signal. So here, if you were in the scenario on the on the left side, when you transmit the signal and you receive, you sense the received signal from A and B, and if they are both at the same phase, then you won't be able to detect the difference between the two. However, if you think about it like on the scenario on the right, which is the signal is being transmitted in a slanting direction, the shuttle is still flying over the ground. It is transmitting the signal in a slanting direction. Now, if you think about it, this time the signal will take to go from shuttle to B and back is much shorter than, okay, not much shorter, but shorter than the time the signal might take to go from shuttle to A and back. And so if the difference in time is delta t, then the radar imagery, the sensor is in fact latching on to the information in delta t in its sensing. So it's all about detecting phase differences, and that's how you detect different features on the ground. So if you are not able to detect the phase difference between two features on the ground, like in the scenario on the left side, then you can't tell them apart in the imagery. But if you are able to tell the phase difference apart between two targets, like on the right side, you will be able to tell the two targets apart. So this is again, this is one more fundamental difference about how optical imagery and radar imagery are different. Radar imagery, it actually looks for the phase differences between the transmitted and the received signals, and so that's a fundamental reason why the shuttle also has to look in a slanting direction, and that is a fundamental part of how radar imagery is sensed. And like we'll get to, there are a couple of consequences of this as well. But for now, the point to note is optical imagery are typically down-looking sensors. But since the electromagnetic spectrum that they operate in is very different, that's okay for those. But for radar imagery, that doesn't work because they won't be able to resolve targets that are at equal distances from the shuttle. But that can be fixed by looking in a slanting direction, which is what the SAR data does. Couple of points to note: the larger the antenna on the shuttle, the finer the spatial resolution on the ground that it's able to latch onto. So you can think about it as an aperture. So if the aperture is large, you will be able to decipher smaller resolution, finer resolution on the ground. But also, if you can think about it, there will be practical constraints on how large an antenna you can mount on a shuttle. So in order to not be limited by that, scientists use complex signal processing techniques and motion of the shuttle itself and all of that to synthetically build a large aperture sensor. And so that's where the synthetic word in the synthetic aperture radar comes from. The aperture that actually manifests is synthetically derived, and it's much larger than the physical antenna that sits on the shuttle itself. Now, getting into a little more details, Dhritiraj, can you go to the next slide, which is called main aspects of SAR imagery? So in this, I wanted to highlight a couple of main aspects that determine how the signal turns out. So the sensed imagery turns out. So the two main aspects are transmitted signal and the target characteristics. Transmitted signal, there is the wavelength polarization and the incidence angle, and target characteristics, there are topography and roughness of the surface and directed constant of the target. We'll get into a little bit of details with each of them. But the wavelength and polarization of the transmitted signal will determine the scattering from and penetration into the target. The incidence angle of the signal will determine the image brightness. Target characteristics, of course, determine what the backscatter is. That's how you think about the reflected signal in radar terms. So the backscatter from the target is determined very strongly by the topography, surface roughness, and so on, and dielectric constant of the target. Next slide, main aspects of the radar signal. In this case, in this slide, the transmitted signal characteristics. So here's a picture showing wavelengths, increasing wavelengths on the horizontal axis and different targets on the vertical axis. If you think about it, the larger the wavelength, it turns out the penetration into the target is deeper. So as you use higher, longer wavelength signals in your radar, you will be able to sense characteristics of the target deeper and deeper under the surface of the target. So low wavelengths, the reflection and backscatter will be from the top surfaces. Medium level wavelengths, they'll penetrate a little bit, and long wavelengths actually penetrate quite deep into the target. So this has, so depending on your application, you might use different wavelength radar imagery. So it might be whether it is dry snow, whether it is alluvium or vegetation characteristics. You might want different wavelengths for different aspects of those that you might be interested in. So for example, if you want to just detect forest presence versus absence, you might use one particular wavelength. If you want to tell forest types based on vegetation structure and all of that, you might want your signal to actually go deep into the vegetation structure to derive information from there. So you will use another wavelength. And similarly, you might be interested in soil characteristics, features deep under the soil, snow characteristics, and features deep under the snow melt, and so on. So different applications take different wavelengths. Also, there is the concept of polarization in radar. That's also a whole world in itself. I didn't want to get into that now because of it would be beyond the scope of the introductory material I have here. But that's another thing that is worth getting into as well. This is again polarization of electromagnetic spectrum. If you remember from your high school days, it's basically the same thing: horizontal and vertical polarization at transmission and receiving phase. So depending on which combination you use, you will have different information sensed as well. And of course, there's the incidence angle, which affects the image brightness. The other aspect is the target characteristics aspects, which is in the next slide. Main aspects, target characteristics. So this will determine the various backscattering mechanisms. On the right side is the cartoon showing some 4 main different kinds of backscattering. So if you have a smooth surface, the reflection might be almost perfect reflection, and that will be specular backscatter because hardly anything comes back into the signal, into the sensor. Almost everything reflects away from the sensor. If you have a target which has 2 phases to it, the transmitted signal may bounce 2 times off of the 2 surfaces and come right back, and much of it will come right back. So this might look quite bright in the image. That's double bounce. If you have a very rough surface, of course, the signal will scatter in all directions. Only small part of that will reach back the sensor, and that is rough surface backscattering. And in some cases, the signal will penetrate deep into the target, and depending on the structure of the target, it will scatter multiple times within the target itself, and then some of it will come out and come back into the sensor, and that's volume scattering. So these are 4 main kinds of scattering that you might encounter at surfaces on the ground. All of this is also determined, all of these are also interact with things like density of the target on the ground, dielectric constant on the ground of the target on the ground. This is basically how much water content there is in the target, the size and orientation, and of course the wavelength of the signal that we've been talking about. So the dielectric constant, which is the water content, affects the absorption of microwave energy and hence affects the backscattering. Next slide, which has additional factors that also influence the signal sense that is sensed. These are advanced topics. I didn't get into the details of them, but I just wanted to put them here so you can explore them in your own time. Additional factors that determine the signal that is sensed is distortion and noise. Like all transmission and sensing systems, there might be distortions due to geometrics and the radiometrics of the optical system. So radiometric is basically signal might be of different strengths in different parts of the swath. So the transmission and reception will be different depending on where in the swaths the target is. Geometric distortion, this is mainly because the slant direction, the view, the look direction is slanted in radar imagery. So that will lead to features like slant range distortion, layover distortion, and layover and foreshortening, shadows, and so on. And then there's the other source of noise, which is speckle noise, which is basically because of multiple constructive and destructive interferences between the scattered signal from the target. These are all so radiometric and speckle noise and the causes for those, and all those might be might get into details of electromagnetics and so on. Those are beyond the scope of this talk, and also beyond this. I'm not an expert in those. But geometric distortions, these are more geometric, and if you think about the imaging angles and so on, these are easier to understand. You could check these out in your own time. Lastly, I wanted to leave you with just some broad hints on so we talked about how different wavelengths are used for different applications. All the concepts we talked about so far are common to whichever wavelength you might use, so it doesn't depend on which wavelength. All of these concepts apply for all of them. But when you think about your application, you might want to think about what wavelength you want to use. And here is a table that's indicative of that. So it could go from low frequency, high wavelengths to high frequency, low wavelengths. And here's a table. So for example, if you're interested in agriculture and surface characteristics of forests and soil moisture and all that, you might want L band, which is in this frequency range. If you want to think about agriculture and ocean, it will be in this range, and then so on, glaciology, forest biomass, and things like that. Commonly used bands for forest vegetation monitoring, for example, is L band. Forest structure, the canopy structure would be C band. X band is even shorter wavelength, so it would reflect off of the top of the canopy. And just as a pointer, you might have heard of datasets called Sentinel-1 and Pulsar. These are both radar imagery. Both of these are available as datasets in the Earth Engine catalog. Sentinel-1 is the band, it's a C-band radar, and it's more for ocean and agricultural applications, and Pulsar is more for forestry and soil moisture and stuff like that. I just want to leave you with a whole lot of resources that's out there that's excellent. In fact, much of what I just now spoke and much of what I have understood about all of this comes from these resources, and I would highly encourage you to go back and check these out in your own time. There's Earth Observation College, which is like an online resource page. So here's the link to that. And the same people have a YouTube channel which has multiple short videos on topic-wise. They're organized topic-wise. And in fact, if you go back to the original website itself, eocollege.org/resources, there's a huge range of full-length webinars and video tutorials running up to 45 minutes, 1 hour, which go in depth into the basics, the techniques, the processing, applications, and all of these. I would highly encourage you all to go in there and take a look. And lastly, just a few additional resources with documents, written stuff. So there's the recently released Surveyor SAR handbook for forest monitoring and biomass estimation. The link is all embedded in that. There's a technical report from WWF which talks about satellite remote sensing for conservation. This has both optical as well as radar. And then there's the real technical, the paper that describes the full technicalities of the SAR imagery, which is also linked in here. That's about it.